Let's imagine a fluid flowing in a pipe to be composed of several concentric cylindrical layers as the figure shows. To this point, we have considered the fluid to be ideal with no viscosity. In this case, each layer of the fluid moves at the same velocity, even the outermost layer that is in direct contact with the inner surface of the pipe. However, when the fluid has a viscosity, then the fluid layers move at different velocities. The fluid at the center of the pipe has the largest velocity, and the outermost fluid layer in contact with the inner surface of the pipe doesn't move at all because of strong intermolecular forces. So strong are these forces that if it was the solid surface that moved, the fluid layer in contact with the surface would move along with it. To help introduce viscosity in a quantitative way, let's consider a viscous fluid between two parallel plates. The top plate is free to move, while the bottom plate is held fixed. If the top plate is to move at a velocity v relative to the bottom plate, then some force F is required. For a high viscosity fluid, like honey, a large force is required. For a small viscosity fluid, like water, a smaller force is necessary. As the drawing shows, we can consider the fluid to be composed of many thin, flat layers. When the top plate moves, the layers between the plates will slide over each other. The velocity of each layer is different, changing uniformly from v at the top plate to 0 at the bottom plate. This kind of flow is called laminar flow, since each layer is often referred to as a lamina. As each layer moves, it is subjected to viscous forces from its neighbors. The purpose of the force F is to compensate for the effect of these viscous forces, so that each of the layers can move at the same velocity. The amount of force required depends on several factors. Larger areas A, being in contact with more fluid, require larger forces, so that the force is proportional to the contact area. For a given area, greater speeds require greater forces. Therefore, the force is proportional to the speed. The force is also inversely proportional to the perpendicular distance y between the top and bottom plates. The larger the distance y, the smaller the force required to achieve a given speed for a given contact area. We can combine these proportionalities into an inequality by multiplying by a constant term. The proportionality constant, eta, is known as the coefficient of viscosity, or simply the viscosity. We can now state the following. The magnitude of the tangential force required to move a fluid layer at a constant speed v when the layer has a surface area A and located a perpendicular distance y from an immobile surface is given by eta v over y, where eta is the coefficient of viscosity. The SI unit of viscosity is a Pascal second. Another common unit of viscosity is the poiseuille, which is equal to 0.1 Pascal seconds. The value of the viscosity depends on the fluid and often on the temperature. You probably know from experience that if you heat a very viscous fluid, like honey for example, it will flow more easily. An ideal fluid has a viscosity equal to 0. Viscous flow occurs in many situations, such as oil moving in a pipeline, or water being forced through the needle of a hypodermic syringe. The following figure identifies the factors that determine the volume flow rate Q in meters cubed per second of the fluid. First, in order for the fluid to flow in the pipe, a pressure difference must be maintained between any two locations along the pipe. In fact, Q is proportional to P2 minus P1. Thus, a greater difference in pressure creates a greater flow rate. Second, a longer pipe offers a greater resistance to fluid flow, and Q is inversely proportional to the length L. Third, high viscosity fluid flows less readily than low viscosity fluid, and Q is inversely proportional to the viscosity eta. Finally, Q is larger in a pipe with a larger radius. The dependence on the radius r is surprising, as Q is proportional to r to the fourth. Putting these proportionalities together, we arrive at Poiseuille's law, which states the following. A fluid, whose viscosity is eta, flowing through a pipe of radius r and length L, has a volume flow rate Q given by the following expression, where P1 and P2 are the pressures at the ends of the pipe. The fact that Q is inversely proportional to L has important consequences for long pipelines, such as the Alaskan pipeline. The pressure drops along the length of the pipeline, and long pipelines must have pumping stations at various places to compensate for the drop in pressure.